font is this small. Let me get this bigger. 1 second. So if I have this matrix A, so I want to define a 1000 by 1000 matrix. So that's a lot of entry for me to type in. I need to type in like 10,000. What is 100 by 100? That's 10,000. That's 10,000 elements, right? So in MATLAB, what you can do is you can ask MATLAB to generate a 1000 by 1000 matrix with each element to be a random number. So to generate that, you just do rank 1000 by 1000. When you do this, you will get a matrix such that each element of this matrix is a random variable. It's uniformly distributed random variable between 0 and 1. When you do this, now you have a matrix. So this matrix A, so you can see like what's the size of matrix A? It is 1000 by 1000. And similarly, I want to solve for AX equal to B. I can let B to be a vector of random components. So I can rank, say 1000 times 1. So I want B to be a vector. That's 1000 rows times 1 column. So if I do that, I can get this column vector that has 1000 elements. And now I want to solve for AX equals to B, right? So you cannot really ask MATLAB to do something like this. If you do this, it will complain. It's like, what do you mean? You have an equation, you have an equal sign in here. In MATLAB, to solve this is very simple. So the equation we're trying to solve is AX equals to B. Another way to write this is that X vector equals to the inverse of A times B vector, right? So the inverse of A is also 1000 by 1000. In MATLAB, instead of doing the inversion, you can simply tell MATLAB X equals to A backslash B. If you just want to solve linear system and you don't want to know any other programming language with MATLAB, it's just this simple. It's A backslash B, and you can get the solution. So this X, you see every element is pretty much all random, but if you do whose X, it's also 1000 by 1. That means you can get 1000 solutions in such a vector form. So what is behind this backslash is exactly Gaussian elimination. So this it uses the algorithm of Gaussian elimination to compute a 1000 by 1000 system so fast. And in fact, we're going to learn how do we write down such an algorithm, and how do you implement this yourself instead of using the built-in package of MATLAB. Let's solve a large linear system. So let's see, what if we're dealing with a discrete Laplacian? So we want to deal with such a matrix D. We want to find all of its eigenvectors and eigenvalues. So in order to generate a matrix D that is 1000 by 1000, I don't want to type in like all those 10,000, all those 100,000 elements. So what I wrote a little code here called D2. So I can generate this discrete Laplacian simply by typing D equals to D2 of 1000. So here D2, as you will learn later, it is a function. And this function takes one variable that is a number, that is the size of this matrix. Because I want it to be 1000 times 1000, so I put in this 1000. If I do this, you'll see generate a matrix. It's pretty much 0 everywhere, except for all the tridiagonal elements. You see you have this marching band of numbers. It's 1, negative 2, 1, negative 2, goes down like this. And it's 1000 by 1000. I want to get the eigenvalues and eigenvectors of it. So MATLAB also has its own built-in function to do that. So I can take the eigenvalue and eigenvectors by doing this function EIG of D. So if I do this, it returns two matrices. One is a matrix P that stores all the eigenvectors. So each column of this matrix is an eigenvector associated with one eigenvalue. And all the eigenvalues, they are stored in this matrix Q. This matrix Q is a diagonal. It is a diagonal matrix, and along its diagonals are all the eigenvalues. The reason it's written in such a way is because of the eigenvalue decomposition. Because in this case, so you see the command at 1 is P and Q equals to eigenvalue of D. So what MATLAB want to return is that E equals to P times Q times P inverse. So this is a regular form of the eigenvalue decomposition you see in linear algebra. And here Q is a diagonal matrix, exactly what we got over there. And you see in this case, for MATLAB, it takes pretty much no time. You just run this and immediately you have the answer of what is P and what is Q. So there are some algorithms so efficient that for 1000 by 1000 matrix, pretty much this is not even a good computer, it's my old laptop. And it can pretty much tell you the result instantaneously. And also, if you try to break this, you can make it even bigger. Let's say what is 10,000 by 10,000 discrete Laplacian. How long does it take for the eigenvalue decomposition of that? So I generated that. I do eigenvalue decomposition. Now it's gonna take some time because this computer is pretty old. Actually, I don't have a good estimate of how much time it's gonna take. Oh, now it's finished. So it computed all the eigenvalues and all the eigenvectors. So for such examples, how you see here, I'm using the functions that's built into the program. If you use Python, if you use other language, usually you have those functions already built in. You don't have to don't have to write a code to get all the eigenvalues and eigenvectors. But in this class, we'll show you what is the inner work of those functions. How do you write your own function to find all the eigenvalues and all the eigenvectors, and why do such an algorithm, why are they efficient and why are they stable? Okay. Once again, if you don't know what's going on here, if you don't want to play with MATLAB, don't worry about it. And our station leader, she's very good at it, and she'll show you how to use MATLAB. Okay. And in those two examples, those are for very large matrix. How do you manipulate them? How do you get their inverse, and how do you compute the eigenvalues? So